Hello and welcome. My name is Schrammel and I'm going to present you our paper Donky domain keys efficient in-process isolation for RISC-V and x86. So modern software is incredibly complex. It often consists of closed-source third-party libraries with potential unknown vulnerabilities. For example, web browsers. They handle both sensitive information but also run untrusted code. And they're built on top of dozens of libraries for media decoding, font shaping, etc. In fact, Firefox and Chrome are the top two applications with the most number of CVEs. So there's an ongoing effort to rewrite libraries in safer languages or split the browser apart into multiple processes. All of this requires a lot of engineering effort, and it also means runtime overhead. So it is clear that we need efficient sandboxing. So software can be sandboxed using various different techniques. For example, it can be kernel-based with separate processes. This offers high security, but also a high context switch cost. There's other kernel-based in-process isolation techniques. However, they also require heavy kernel modifications. And sandboxing can also be done entirely in Userspace. For example, using software fault isolation as done in native client, or based on protection keys like Ariane does. They typically offer fast context switches, but typically incur a small runtime overhead. So what are memory protection keys? So pages are tagged with a so-called protection key, which is stored in the page table entry. In the case of Intel-MPK, we have 4-bit keys and thus 16 possible keys. And there also exists some policy register which stores key permissions for each of the keys. For example, here we have the key 2 and 3. We have set all of the read and write disable bits, so the bottom two pages can no longer be accessed. And this register is user writable, so this allows us to quickly change memory permissions from the user space. Now, how can we build sandboxing using MPK? Or protection keys for user space? We need to make sure that the only safe call gates modify this policy register. So, for example, a sandboxed application must not be able to change its own permissions. This can be done using binary scanning and rewriting, in addition to write XOR execute. Furthermore, we have to limit syscalls that may be able to bypass or circumvent this protection. For this, we need a kernel module or, for example, ptrace process. So previous work has already shown that this works, for example, Ariane or Hodor. However, there are some open questions. For example, can we sandbox self-modifying code, JavaScript compilers? Can we have protection key-based sandboxing without the binary scanning? This brings us to our work. We have designed protection keys for Userspace from the ground up on RISC-V with in-process isolation in mind. We repurpose the RISC-V extension for user-level interrupts. This is an ISA extension which is currently in a draft status, so it is not yet finalized. And we propose some modifications to it. First, we limit the registers related to this interrupt handling so that only the interrupt handler itself can modify it. This gives us a trusted user space exception handler, a so-called monitor. This monitor is also able to intercept syscalls directly in user space. This is possible because on RISC-V, syscalls are implemented as exceptions. And this extension for user-level interrupts can also delegate exceptions directly to this user space handler. On RISC-V, we have page tables with 10 free bits. We can use all of these bits for protection keys. This gives us over 1,000 domains. However, we cannot keep all of the permissions for these 1,000 domains in a register. So we designed the policy register to hold only 4 key slots with their read and write permissions. And also this register can only be written from the monitor. So let me give you a quick overview of this. Here we can see a user space application with the monitor as well as a domain. So the monitor, once the process starts, sets itself up and protects its own data with a separate protection key, here with the number 1. And then the domain A, which may be used for the main program, also gets a separate protection key to protect its private stack, here shown as 2. And as previously mentioned, any syscalls that are made are automatically intercepted by this monitor, which can then filter them based on a per domain basis. Now let's assume we have a second domain in this process, so-called vault, which may handle sensitive information. This vault is set up so that it has its own protection key, number 3, as well as read access to the domain A. So that means that the vault can access the data from domain A, but not the other way around. Now let's assume we have another domain which may run malicious code. We don't want it to access any other data or the other way around, so it only has access to its own protection key, number 4. Now, if they want to share memory, they can create a separate shared memory area, which is protected with a separate protection key, and we give those 2 domains this key. Now they can safely share private data without domain A knowing about it. But how do we switch between domains? For this, we have defined so-called dcalls. Dcalls are basically function calls which call into predefined entry points into domains. This makes it possible to run code with the permissions of another domain. Now, let's look at an example how this works. So here we can see domain A and B. Domain A initiates the dcall and wants to run code within domain B. For this, it also starts with the stack pointer pointing to its own private stack, which is protected by its protection key number 2. So it starts with calling a simple wrapper around the dcall function, which saves all of the registers. This is necessary in case the domain B is malicious and tries to corrupt or read these registers. Then this wrapper calls into the monitor, our Userspace exception handler, which then loads its own private stack. It does some security checks to make sure that domain A is allowed to call into domain B. Then we create this separate stack for this domain B. We update the policy so that we can access domain B. We switch the stack and finally jump to the target domain. Here we also have a small wrapper which simply makes sure that we return to the monitor once the function returns. Once in domain B, we can execute any code. However, we are restricted by the access policy register, which is only the key number 3 loaded. So we cannot access any memory from domain A or the monitor. Now, once the domain is done and wants to return, we go back to the wrapper, which calls the monitor. Then we switch the stack again. And the same process starts again. We do the security checks to make sure that the domain B is allowed to return to domain A. We update the policy register, switch the stack back, and go to the wrapper. The wrapper then restores the register state like it was before the function call, and then we're back after the function call. So Donky is implemented as a hardware-software co-design. We proposed a small hardware extension for RISC-V based on the standard extension for user-level interrupts and implemented this on top of a RISC-V CPU called Ariane. And also part of this implementation is a software library where we have defined an API for managing the domains, keys, as well as transitions. We also wrap some standard library functions for memory management, threads, and signals. And it is also compatible with Intel-MPK. We have evaluated Donky on a RISC-V CPU and as well as CPUs with Intel-MPK. So the most important number here is the domain transition overhead. How long does it take to transition from one domain to the other? And here we can see it is around the same time of a simple system call. And compared to a process context switch, this is orders of magnitude faster. Now, if we want to isolate CPU-intensive code, it runs with almost no overhead. There's only an initial overhead for the setting up of the domains as well as the security monitor. When isolating simple cryptographic functions using mbedTLS, we can see a small overhead of 0 to 15%. We have taken the fastest of these operations, which was Poly 1305, and used the smallest possible block size. And even for such a fast-running operation, Donky is only 3 to 5 times slower. If we would now isolate the same function using process isolation, this is 14 to 110 times slower. We also isolate Google's JavaScript engine, V8, and can only see a small overhead of 0 to 2%. So in summary, we have shown you an efficient and secure in-process isolation mechanism. We can switch to domains and filter syscalls entirely in Userspace. We have 0 overhead within a domain and a very small switching overhead. We do not require any binary scanning, write XOR execute, or control flow integrity. We support easily self-modifying code, so JIT compilers, and have configurable trust relationships. We also support over 1,000 possible domains or sandboxes. And of course, our implementation is open source on GitHub. Thank you for your attention.